Good. I'm Patel. I work for National Institute for Computational Sciences, and today I'm going to present introduction to GPU programming. Uh, lecture it will be a little bit longer than the usual one, so it may end 3:15, 3:20. And in weeks we will have a talk on advanced CUDA programming as well as OpenSCC, right? So start with the outline. So I'm going to introduce the motivation behind designing the GPU hardware. Why we came up with this rather than the CPU. A little bit history about GPU and how it evolved. And then after, I will talk about GPU architecture, specifically NVIDIA GPU architecture. After GPU programming model, we will introduce the architecture and the memory model for NVIDIA GPU. I will run the CUDA example, how to write the simple CUDA example, and some information about CUDA tools like the Docker, debugger, and some of the CUDA libraries which are available. So let's start with like why had this GPU hardware. So we had CPU and applications like physics, artificial intelligence, and networks. Those were the highly CPU loaded applications. For graphics, for the visualization, we need fast memory access, because if you vertices normal structure, it needs to look up to the memory, and CPU could not to help in that condition. And we are other important thing was the cost, because matrix vector products or multiplying the vertices or texture, it takes a lot of computational power. But it needs to have the memory access from the disk, but it needs to have the access from the RAM. So even for matrix vector product, it's about 5 gigaflops of. So it's like if we need to have the real-time graphics or visualization, we need to have the space hardware, CPU and what. So CPU is designed to rapidly manipulate and memory in such a way that build the images in frame buffer and put it on the display. Came up with this word CPU in 1999. So that's the history of graphics hardware. So 1990s, they had this mainframe and workstation actually designed for graphic and visualization. And we had some PCs which only supports the 2D graphical display. In mid Macros and ATI came up with this 3D graphic hardware, but still it's like the very specialized personal computer. They came up with the car, which you see on the right hand side, like maybe twice a your credit card. So they came with this card which can do the transform and the lighting, and you don't have then spatial workstation for visualization and graphics. And graphics hardware, there are two main leaders, NVIDIA and ATI. Years back, and this hardware now being used in many gaming console like Xbox, PlayStation, and so on. So what is GPU, right? So GPU means the general purpose programming on graphic processing unit. General purpose is not like viewing the images or doing some visualization or fancy graphics, but scientific application like the linear algebra operation or some kind of Cholesky factorization or something like that. And most of and GPU is really helpful when you have the data parallel algorithms because it works based on single instruction multiple data. So if you have single instruction and wants to operate on multiple data, it improves the performance a lot. And this is the website gpgpu.org. It's really well-known website for GPU applications. So you can go there and look at the application people have developed and find the research papers and so on for GPU stuff. So here the graphs. One is on the left-hand side is for the different processors and the theoretical peak value for it. And on the right-hand side is the different processor and the theoretical gigabytes per second memory access, the memory band. So on the left-hand side, as you see, the NVIDIA, the latest one is NVIDIA GTX Titan. Single precision, it gives you about 4.5 teras per second. And if you look at precision, that's the K20X, it gives you about 1.3, 1.2 teras of data. Intel as well, single precision is less 1 teraflops, and the double precision is about 0.5 teraflops. And if you look at the memory bandwidth, the GeForce GTX Titan, it has the memory bandwidth about 285 gigabytes per second. From NVIDIA, which is less than 60 gigabytes per second. So you see how this can be, means how it means it's really helpful to do some data parallel operation on few hardware. Because memory bandwidth is 4 times faster. The theoretical peak is also 2 times faster. So the GPUs are very efficient for manipulating the graphics and highly parallel structures. This makes it more acceptable to use in the scientific function because that way we can have the highly parallel data algorithms and we can run much faster on GPUs. And these are in terms of the architecture, it is a massively multi-threaded manipulation. Here I shown the specification for NVIDIA Tesla product. The latest one is the K20, and they are coming with Maxwell. But this one is the Tesla, which is 3-4 years old, but it has 512 cores on the chip and about 655 gigaflops, double precision performance, gigabytes of memory, and memory bandwidth is up to 177 gigabytes per second. And across the science and engineering disciplines have been achieving very good speedups on GPUs for some of their algorithms.
Speed up by on the application because we didn't very well at the start of the or I'm not forced test-based programs on the chemistry the one from one math so the also to hybrid programming. So then those who brought not that very good job with OpenSD and NPI, and then applications are having developed, which I believe just because they didn't do a good job.
There are many factors. One of the factors I can think of is some of the algorithms you can achieve the speed of a certain threshold because those algorithms cannot be parallelized or cannot scale very well because you need to do too many data operations. So in that case, you need to access the CPU memory and sending and receiving too much data from CPU to GPU, and you spend more time in data transfer rather than doing actual computation. So I don't know what algorithms they have in the madness, but it may possible that because of this limitation, they could not able to achieve the speed of beyond 2 twice or 3 times. Once you just send data to the GPU memory and then you do all the computation, and at last you just send the results. So more time in computation rather than doing the real. So NVIDIA has this three different categories for their GPU products. One is called desktop GPUs, another one is called mobile GPUs, and third one is workstation, is mostly the high performance GPUs. The G4 series for desktop and mobile, and they have Quadro and Tesla series for workstation. Now they have the K series and Titan series for workstation as well. NVIDIA GPUs, they support both CUDA language as well as OpenCL library. As I mentioned, they came up with this Kepler in 2012, and they are coming with Maxwell in 2014. And we also have three different types of categories for that product line: desktop, mobile, and workstation. Radeon series are really popular for desktop and mobile devices. And Fire Pro and Fire these are the Tesla or NVIDIA A20. But the important thing about AMD GPUs, they don't support CUDA or OpenCL library. So you cannot follow on AMD GPUs. So let's talk about GPUs in terms of supercomputers. What people are using in supercomputers. So typical supercomputer, it looks like it has large number of nodes, 20,000 nodes, and each node has 12 cores and 16 gigabytes of memory. So we have like 12 cores per node. It has net, so nodes can transfer the data fast. And the pro model for this type of supercomputer is AI or maybe hybrid, which combines TI and OpenAI for MPI and ether. Now, when we talk about a supercomputer, that means each node may have supercomputer attached with it. And in this, it's going to increase your floating point performance by 10 times, memory bandwidth by 20 times, and the parallel per node is in order of 500 cores, because even if you take an example of NVIDIA Tesla, it has 512 cores. And just another accelerator, it's becoming popular. It's from that is called Intel Mine, called many integrated core. Right now it has around 63 core per node or per chip, but this is the x86 cores. So what code you have running on your laptop, you can Intel accelerated card. But the best performance compared to the the Intel ID parallel code. So come up with this product in 2012, and there are some other accelerators can be possible to attach with the node like FPGA, that is a field programmable gateway array or digital signal processors, and you can make this accelerator supercomputer.
Yeah. and probably very more than 50. So here, you know, have working back on that you have where
Right.
uh,
So I like that means that that was the impression when they launched this in the advertisement and we called Beacon, which has the mic on. What we are seeing is, yeah, I can run my application on mine, but some applications are running slower than running on the one node optimized for that part, right? So you run the application, but you cannot actually use the available resources on that part, and you have to optimize your code for that particular part. And so they have this special OpenMP pragma. They have this still programming language that you have to use and do the proper way, like transfer the data, access the memory, and optimize for those 400 threads and so on. So impression when they launch it and say, oh, yeah, I mean,
without to be true, right?
right. It means some of the things like we just routed onto that Intel mic card, it was then running on the single. So there is some code. Okay. But can you run it efficiently? Right? Okay, so the GPU architecture is not for all the applications. If you have the top level parallelism in your code, then it's not best to use the GPU, but if your data parallelism kind of application, then it's preferable to use GPU. And the thing is, operation needs to be sufficient size to overcome the overhead of memory transfer. So if transmitting data rather than doing the computation, then you won't just speed up in your code because you're spending too much time just accessing the data. So let's talk how it's different CPU in terms of architecture. So on the left you see the DRAM, cache, unit, and ALU unit, right? That CPU, like typical CPU. On the right you see the GPU DRAM. It has the control unit and the arithmetic units, but CPU is specialized for computational intensive applications. It devotes more transistors for the data processing rather than caching and the flow control. So if you have more operations to do, and it has many transistor allocators just for data processing. And the important from some of them like device and code. So when one talks in CPU code, like, oh, this is the device and this is the code. The device always means the GPU part and means CPU. And it runs threads in parallel. The another important term is kernel. So when one writes the GPU code, then one computational intensive part which will running on GPU is called kernel. So kernel is on device. The another difference between GPU and CPU is GPUs are extremely light. Really low overhead for creation of, while the CPU thread has more overhead than the GPU thread. Another thing, you need to use thousands of threads to efficiently use one CPU. If you have 4 cores, you efficiently use that 4 core using 4 threads. On GPU, that's not the case. And I'll show you in later slides why it's not the case. Even say 500, it has 512 cores, and it's on 512 threads, still it will efficiently use all the available resources.
Okay. With respect to number of threads, so will you expect to see some sort of application with so many things in the offering have and other.
Oh, I went like how large your matrix is, right? So like if you are on like 100, if you have 100,000 elements in your matrix, um, the third concept works is like number of grid size and number of block size.
Okay.
So I will show you later like how it is. Generally, as far as I know, it should be like 100,000. So here how CPU and GPU work together. So step one is you copy your, let's say, array A from memory to the GPU memory. Step two to do it that array, you may to add the element and get the sum, right? So you send instruction to GPU, and the third will it will execute that range operator on GPU cores, and once it sends the result back to the CPU memory. So this is like the one step when you are in the CPU core. No, sorry, CPU GPU core. So here the GPU architecture. I think this is the NVIDIA Tesla card. This one has 512 cores. Here 16 streaming multiprocessor. Processor has 32 cores. So the total number of cores on this particular card is 512. So let's zoom in and see what they have in each streaming multiprocessor. So processor, it has this PE called the processing element, or we call it as core. And then it has texture memory, constant memory, scheduler. What means the group of threads, generally 32 group of threads called one var. And then local memory and the local memory. So here is some of the programming terminology, CPU programming terminology. So the stage is like it's a ready for execution running operation on the CPU that we call it thread. And the group of 32 threads. Block is group of var, and the block one multiprocessor. The group of blocks, and the before is the CPU and UI is CPU. So you have this thread, var, block, and group. Let's look at one by one how multiprocessor looks like, how the memory looks like. The multiprocessor figure like each multiprocessor has multiple processors in it, right? So each multiprocessor is a set of 32 processors with the architecture. And clock cycle, multiple processor execute the same instruction on a group of threads, which we call var. You see this now here it represents how the memory is connected with each processing element or processor. Here can be execution var size equal to number of threads. Multi-threaded execution across the different instruction streams within the block. Each box maps to the single streaming processor. So there is no direct interaction between the streaming processors. Here is the memory layout. Like each processor has its own register. Each multi has the shared memory. And processor within the one multiprocessor can access the shared memory. constant memory. Each multiprocessor has a constant memory, but that's the read only. Texture memory, which is also the read only. This device memory which can be accessible by all the multiprocessors. Means like processor 1 to multiprocessor all can access memory, and also can access this device memory. But as constant texture and shared memory are accessible within the multiprocessor. So register is a read and write per thread. Local is also read and write per thread. It is read and per block. It is read and write per grade. It is also only read memory, and that is also only read memory. But the write and read local, constant, and texture memory. So these has multiple blocks, and each has multiple processing units. For each block can have multiple threads. But within one block cannot able to access the shared memory of another block. Within one block can access the global memory. Now, how we can use architecture? So there are different ways you can use this architecture and application, and how much effort you want to put into writing your code or using this architecture. So this thing GPU software you can use, and you don't need to worry about writing your code or anything. Just use that code, use that application, run it, and you get a performance improvement, and you don't need to worry about how to write a CUDA code or anything. Let's say you have the code and you want to plug in some GPU code in it. You can use the linear algebra libraries like Magma or CUDA or CoolFX or CUFFT, and you can easily plug in the GPU code into your application. And if you really want to, if you cannot find the function which are already available in the GPU libraries, then you need to write your own function. In that case, option one, you can use the GPU directives like OpenACC or HMPP or OpenMP 4.0. You need to write the native code, language or OpenCL library. So there are few application which already implemented using the CUDA language, like MANTI, which is the molecular dynamics code, which is also the molecular dynamics code, GHOMER, which is the biology application, TerraCAM, which is chemistry application. So, and there are many others who already who put the CUDA code into their code. So the pros for this is you don't need to worry about implementation or efficiency or performance or anything like that. But this application do not cover all functions, right? Another way, it may possible even if you are using AMD or GROMAX, the model which you want to use, it may not be implemented using CUDA. So in that case, you have to implement your own CUDA version of that model. And yeah, so many applications still immature, so it may not be able to use the latest hardware. It can run Tesla, but it cannot use the NVIDIA's latest K20 or whatever Maxwell will come in this year. So now about GPU programming. So we mostly spend time on what is thread, what is grid, what is block, and how many threads you can execute, and so on. So is executed as a grid of thread block. You see in this figure, like it has device and the host. The host from the executes the kernel. Nowadays you can execute more than one kernel on CPU. Kernel 1 will be executing on grid 1, kernel 2 will be executing on grid 2. And in the block 1, they see the multiple threads on that, right? You can run the kernel simultaneously. It wasn't the case 3-4 years ago, but now you can run multiple kernels on the same GPU. Yeah. So as you said, there can be multiple grids, and each has multiple blocks, and within one block you can have multiple threads. Sorry. Right. Okay, so like the question for online users. The question two states from two different blocks cannot cooperate. Yeah, it's true. As you see here, like the block 1, 0, and block 1, 0, right? Their own memory. And the blocks running within each threads running within each block, they able to access another block shared memory. So you cannot copy. Yeah, the case that if you use the global memory, then they can. Yeah, they can. By default, yeah.
This problem
I mean, you can do that, but you have to actually specify those by when you connect. That means they cannot access it. If you have something, then you need to explicitly say once you done this work, copy the data on global memory, and then say kernel to access that data.
which is what
Yeah, I mean, if you use the shared memory within the block, so that way you don't need to go and access the global memory. But if you have to, then you can use the global memory. Shared memory is faster access than the global memory. Here, like the grid 1, it has this block 1. So how IDs and block ID work? So it's like it can decide what data to work on, and the block is going to be in 1 dimension or 2 dimension. Say like it can be 1 dimension, 2 dimension, or 3 dimension. So how the thread hierarchy looks like? So it is like the 3D ID, unique, and it's 2D and unique in grid. And you set this dimension when you launch the kernel, and will determine the thread. It's going to be like number of blocks multiplied by number of threads per block. There are few building variables for device code like thread IDX, block IDX, dimension, and the grid dimension. These are useful when you want to access the particular element of that array. I will show code how it's useful to use thread ID, block ID, and block dimension and the grid dimension. At least we know like how the GPU architecture looks like, and the main terminal was before GPU program like host, device, thread, board, ID, and block ID, grid, and so on. So CUDA, it's called basically Concrete Unified Device Architecture, extension of C++ language, and DGI has developed the thing for Fortran 2003. And it has two APIs. One is called the runtime, and another one is called drive. So when you run your code, you need to first figure it out which card you have and the device driver you have on your machine. And then you need to download the CUDA SDK, and then you're good to go. Means you can write the code, compile, and run it on your CPU. Card, they don't support the CUDA 5.0. So, and here are the few of the CUDA applications, like where it has been used. So it's been used in computational geoscience, medicine, computational finance, as I mentioned, NAMD, GLOMAS, DACAM. It has been also used in computational modeling, computational biology, like Homer, and all this. So here idea of CUDA software, how it looks like. So on the left, the first box says CUDA optimized library like FFT, BLAST, LAPACK, libraries, and so on. So those are libraries for CUDA. And you have this integrated CPU GPU code that is top level. Then after, you have this NVIDIA C compiler. We will compile the code into NVIDIA assembly language, PTX parallel thread execution assembly language, and then it will convert your CPU code into CPU host assembly language.
So it's like with your force filling being compiled to differences?
Yeah.
Okay.
It splits your code into two different CPU categories and then compiles CPU code into CPU assembly and CPU code into PTX assembly language.
Okay.
And then for the CPU host code, it just use standard C compiler like GCC or CGA or Intel. Compile code and run on CPU. But then the parallel execution assembly code, then you use the CUDA driver and the GPU. Sorry?
Different you have to recompile it on different architectures. You can the more.
Oh, God.
Yeah.
I think you have. So, yeah. Right. Right. So you need to recompile your code and do you need to recompile your code when your car go different machine? Yes, you have to recompile your code. So, intro about CUDA C extension life. When we talk about C, we need to talk about the data types and the functions and the return types and some of the functions. So here it has the qualifier, it has some built-in variables, intrinsic like sync thread, and the REI for memory management. It's like qualifier. It can be device, it can be global, it can be shared, local, constant, and many others. So an example of device, when you say __device __ float array 28, that means going to allow the device and callable by D. When we standard for global and for void, that means that function will be allocated on the global memory and can be called by CPU. Then the variables like IDS, block IDS. And it has fixed like if you want to do the all synchronization of all threads, then you can call sync threads and it's going to synchronize all threads. For memory management, it has like CUDA malloc, CUDA free, CUDA mem copy, and other functions. And then here is kernel launch. So like your GPU code, you need to launch the kernel on GPU, and in that case you use kernel name and then the dimension of the grid and the dimension of the block. It's more clear when I give you an example of CUDA.
So how Arquitecture is now, right?
Yes.
Is that how we do normally do it, or you would rather write your code with placeholders and then?
Oh, you can put variables there.
Right.
If you want. Yeah.
Yeah.
Yeah. Right. So this will make much more clear when I do an example. Yeah. So device. So as I mentioned before, it can execute on the device in callable from global. It will execute it on global, but it can be callable from host. And when you have host, that means it executes from the host and callable from the host. Right? So yes, I'm going to present this simple example of vector addition. How you can do the vector addition on GPU. For CPU, right? Means you have the function and you ask three things, the point of A, B, and C. So then you ask the vector and you want to put the result into C vector and return it back. Very simple CPU code. Let's talk about code, how it looks like. So you use some header files, CUDA.h and the CUDA util, and then you add a vector kernel G code. I will show in the next slide how it looks like. But over there, add the GPU code. And use this integer n with 100,000 elements and 100,000. And then int A, B, and C, which will do the arrays or vectors of 100,000 elements. I want B and store the result in C. So what you need, means the part here, one thing is you need to insert the vector on the whole. Right? So you come initialization like AP equal to sine multiplied by sine and cos multiplied by cos. Huh? This is the CPU code, right? I mean, yeah. And here, I say here, right, add vector kernel GPU code. So I give the file name is CPU code.cu, right? So yeah, the CPU code is here. You see, I initialize this, and that's fine, right? Now, what's the next step? I need that data to the U, right? So here, I allocate the memory. So I say allocate A, B, and C, and so to be N, that is 100,000 elements. B and C on GPU. Then what? I allocate it, but I want to transfer this data, right? Whatever I initialize on CPU. So I need CUDA mem copy, and then this is the destination. This is the source, and it's going to do the CUDA mem CPU host to device. So I transfer the data and data to the GPU. So now vector is vector B on GPU, right? So what's going to be the next step? So now on the kernel. So that is the function call, right? So put that code here. The function call and the definition of the function. Still two things are missing here. and we get some result from this function call. Still the result is on GPU memory. So you went to the CUDA mem copy. Now that is C, and you copy the source, that is the device, to C, and you CUDA mem the device to host, right? So that means to the C memory and free the device A, device B, and device C.
So when you copy the data over that, data from the CPU back to the CPU is override.
Right. Yeah. Right. It's a memory operation, so you can override. Yeah. So now go to the line called kernel. How you call the kernel, and then after I will show you how kernel code looks like. Add one. So my kernel name is A, device B, device C. So my kernel function expects three things: A vector, B vector, C vector. Right? And this is a serial code. I say here the grid size is 1, block size is 1. Execute only on one grid, or only on one block with one thread. This is still going to be serial as CPU code. You won't see any performance improvement. What I need to do here, I say add and 256. So here I number 256. It can be 128 or 64 or 112. But application I have 256 gives you the better result. So you see the blocks in grid equal n divided by 256 or equal to 256. So at these two numbers, it should equal to n. That is your size of vector. Run the grid size n by 256 and run with 256 thread block. And here for vector add, and I say here is serial, right? What I do global. Global means it can be callable from host, but on device. And I use A, B, and C. And this is similar to CPU, right? For I 0, I n, I plus plus, and so, but it's only going to be run by one thread. How in parallel? Let's look at now. So here I here, but I remove the loop. The GPU, they expect all these processing elements are SID, like you just put one instruction and it's going to operate on multiple data. So thread will execute this instruction. You don't have the loop. I say IDX, that determines which thread is going to run this instruction. So it is going to be the thread ID. This is dimension X plus block dimension X multiplied by block dimension block IDX. And that will give the thread number for n divided by 256 multiplied by 256. So each thread will have the different index number and it will execute this instruction that many times. And it asks Misha, like how you can specify the dimension, right, with the kernel. So here you see like the dimension DB and DB. So you have like 150 or 488, or you can have XYZ number. And say dimension X, Y, and Z, and then you specify somewhere in your CPU. So remember, like I said, 2n divided by 256 and 256. 256, I can say something like 4, 8, and 8, right? So specific like X dimension is 4 sets, Y dimension is 4 sets, and Z dimension is 8 sets, like that.
Okay.
And in grid, that is like X dimension block 100 and the Y dimension block 50. Rather than saying n divided by 50, direct saying 5,000.
It's a 5 degree.
Dimension.
Yeah.
And don't specify anything, then by default is 1. In the C, I say add 1, 1, right? That means it's only going to execute by 1. That is serial code. So means
So I think when you specify a message, it's just a number. It's still dimensional, but it has that number for X and 1 for Y.
yeah,
Yeah.
right.
Okay.
And don't specify the 3 dimension and just specify one number, then it use the default number. Like var equal to 32.
Oh.
So yeah, the part here is to understand how to set the release type and the block. And the process, as I mentioned before, it's like the important part of CUDA code. When it's launched, the number of threads per block and the number of polyps are specified. So the total number of threads equal to grid dimension multiplied by block dimension. And well, it's one copy of the kernel. So then you can see the for loop in the GPU code, right? How to compile this code? So you have the CUDA SDK. You use C compiler, which translates your CUDA code into PTX and C code into C assembly language. And etc separates the code for host and device. And I put 2 important links. Yes, you can refer this and you find more information about it, how to do the compilation, and here it has also some examples. Here, scenario where one of you learn how you compile this code. So CC and then you say dash CC bin application of the compiler. So if while it chooses the GCC compiler, but if you want to use the Intel compiler or something, you need, when you say $cc, it will give you the path for the ICC, right? That's why you say dash CC bin. If it's set up by default in your system, then you don't need to give dash CC bin. Use nvcc dash o output file name and your code name. So compile your CUDA application. You just write one code, one file that's called .cu, contains both host code and the GPU code. Here is an example of how you submit the job. It is similar to any other application. You say qsub, and on field line you say number of node equal to 1, processor per node equal to 1, and GPU equal to 3. Because it has 3 GPUs per node, right? So when you request for one node, you still get the 3 GPUs.
Do you have to run it interactively?
No, yes, you can do the back job as well.
Okay.
Yeah. Yeah, and not unless you say number of CPU. Correct. Yeah, question is, can you, if you have multiple GPUs on your node, can you use all of them at the same time, right?
Yes.
So in one case, like, yeah, you can write 3 different tasks, right? Let's say one is factor addition, another is multiplication, and third one is summation or division, whatever, and then you run all these 2 codes on CPU. Within the one program, you can specify this kernel. I want to run this kernel on chip 1. I want to run this kernel on GPU 2, and I want to run this kernel on CPU. And you do within the one program.
This is experiment the different variable
Right.
data.
Yeah, you can do that. The two different systems. Yes. Those are systems. You
You have to
no, you don't need to do different programming. This syntax is for how you request the request. You only need to change this one. You don't change your code. You may to compile your code again different system, but you don't need to rewrite your code or anything. You need to change anything in your code. You compile, and when you request the resource, it may be different. As you see here, on key I say node equal to 1. Why not unless I say number of CPU is equal to 1? That's all.
That is the
Where?
no. Is it?
Oh, no,
Yeah.
you can have the
the number of CPUs and that's
so I cannot request one CPU. I have to request per node. Requesting one node on key.
right. Okay. All right.
On Nautilus,
Yeah, I get that.
Nautilus, I can still, when I say NCPU 1, I will get an 8 cores,
Right.
right?
Yeah, sure.
So,
yeah. You get it.
Yeah, you'll be wasting that.
correct. Unless I have the another slide for that. Unless your CUDA code related with OpenMP, then you use those CPUs, right? Unless if you want to use multiple nodes, you can combine your CUDA code with MPI.
Sure.
Right?
Yeah, you can go through.
So you get 100 nodes, and each node with 3 GPUs, and still you can use all those 300 GPUs if you write the CUDA MPI and OpenMP kind of program.
What is the
Processor per node, you get like 16 cores. So if it has 16 cores, by default you get 16. So you do specify PPM, but this is like if you want to be very, very specific. So I mentioned like you can use like CUDA multi GPU. If you have one node with 3 GPUs, you can do that. Means you can launch different functions on different GPUs. And ask like, are you wasting those 7 CPUs? Means by default, yes. You integrate OpenMP or thread into it. You can use those resources. And if you want to have multiple nodes with multiple GPUs, you can use CUDA PI, CUDA plus OpenMP and MPI. But it's way too complex. You go fast.
and this our architecture has one.
No, the one thing that I mentioned, like, so each socket can have up to 8. So right now that's a driver limitation. If I want with this laptop, I can get 8 GPUs.
Okay.
Up to 8
Okay.
GPUs.
I see. That's why OpenMP works. You decide to take all 8 CPUs, then you can have
Right. Yeah. Database.
So the thread
Correct. CPU core using I want to have this many CPU right? And in your kernel, when you call the kernel, you say, I want to have this many threads for my GPU code. So those threads don't know each other.
There has to be a real application.
Yeah.
You have to go back and learn stuff.
So the help is usually after.
So means if it's OpenMP threads, then you import them for threads to access the CPU memory, but they can access the CPU memory. Correct? So means OpenMP application is similar to the regular OpenMP application. But possible when one your OpenMP thread calls the kernel, right? That means that thread has to wait to get back from the GPU. So it's complicated. Okay, so here are a few CUDA libraries like MATLAB, CUDA, Playback, FFT, Start, Rust, which is C++ template library, program, and the algorithms in this library are highly optimized for CUDA. So you don't need the performance. It's becoming slow in this library because they have put a lot of effort to run this library. And debuggers, how to debug your program. So there are few debuggers are available like Alinea DDP, CUDA, CUDA memcheck. Memcheck is really helpful for if you are getting the wrong index or having memory corruption in your, then CUDA memcheck is really important. Profilers, there are two profilers now in NVIDIA visual profilers to profile CPU code. And I want to mention about how OpenCL is different from NVIDIA. So OpenCL is a free standard while CUDA is from NVIDIA. OpenCL builds the kernel at runtime. OpenCL is not a compiler or it's not a language extension, it's just a library. NVIDIA is an extension of C language. You have to use the compiler to compile the code. With OpenCL, you just need to use the OpenCL library and it should be able to run the code once you can use the regular compiler. And right now there are two main products, one from EDI and another from HMPP. And you can use these directives as like OpenMP directives in your C and Fortran code, like the Pragma, and you run this for looping on GPUs, or Pragma and you run this section on GPUs. It also the directives for data transfer, so you don't need to say CUDA mem copy or CUDA malloc or it is all listed. And these directives, another important advantage of these directives is whatever the directive you have, it can attack it. So worry about whether it's a CUDA OpenCL or CPU, you can say, oh, I have this or I have this architecture, and the directive can automatically identify and convert the code and on the other process. Yes. So I think OpenCL is becoming popular. It's now compiler directives for C, C++, and Fortran, and it's by CGI, CAPS, Cray, NVIDIA. It's easy to use kind of API or directives for GPU programming, and it's becoming popular. The unfortunate part is its specification and it's still not complete. People are updating the specification, so the implementation is not quite available. But you can use PGI compiler and there's many of the features available for the OpenACC specification. We may hope that OpenMP 4.0 will integrate those features. Use OpenMP 4.0 for CUDA programming.
Components for
Right. It has this, yes. It has that. I think what I'm saying is it's here. It means getting the specification. So the documentation not there yet. And I think this is some of the other information. Like if you want the programming with Python, then there are that available like PyCUDA for PyOpenCL. For the main is CUDA toolbox available for MATLAB. Of course, there is a CUDA portion. For our language, there is a wrapper for R1CL and RCUDA. In Haskell and for all other languages, they have the wrapper. You have to use C++, you can use the other language and use this wrapper to run GPU.
Yeah, we can.
Right. Okay. MATLAB and Python and R and so on. These are good resources, and one of them is CUDA Zone. Like you go to the developer.nvidia.com, and CUDA Zone is really popular one. If you want to get any information about CUDA, I give you that the other interesting website where you get all the applications developing CUDA and research papers and so on. About all, then you get the blog. So if any question, you can post in that blog, and there are it's very active blog and mailing list, so you can easily get the answer. Intel come up with the OpenCL SDK, so you can use the Intel SDK if you want to do the open kind of programming. Yeah, I think this is the last slide where some of the rules for fast GPU cores. One is lay down GPU. Huh? So the thing is, the GPU has memory. Right. So that you have to break your data. Right. But develop the out of core algorithm where you don't need to have all the data in memory, but you can access the whenever it's needed from the data. Right? That is always going to. No, the thing is, there is always going to be someone even. Right. I understand, but what my point is, there is always going to be this. If I have 128 gigabytes of memory, then you say, oh no, I have like 100 by 100 million memory. If I say, okay, now I increase my GPU memory to 1 terabyte, now what? And you say, no, still I have this 10 billion by 10 billion memory. Right? So
you miss it for a range of data and
so in what as I know what people do, they develop this out of core algorithms. That means whenever your data and if you cannot fit in the memory, they act hardest. And then yeah, of course, it's going to slow down, but there is going to be the limitation, right? How much memory you can put. Even on the per node, you see like 64, 128, that's all. You can access 1 terabyte of RAM per node.
those but it's also a lot of potential for research. So the initial and default approach for a certain problem maybe try to have everything in memory. So you say probably with the current I know what I can. So then another way.
Another approach. Yeah.
So for example, wrong, they have modified the algorithm from the relation such that they can do block and they do one block at a time. That's always, you need to change the way you do things and code. Different ways to do the thing. So the people very work.
Yes, correct. You have to, yeah, correct, yes, yes, correct, yes.
Better here.
Yeah, it's going to be safe.
Yeah. So if it's faster, here, then
And the thing is, with the serial, you cannot do that type of computation.
Right.
So you have this opportunity to operate with large metrics, right? If you in parallel.
Yeah.
So,
Yeah.
yeah. So these are few of the rules that give the enough work we used to do, and relocate the data for the global memory and whenever possible avoid malloc and you frequently malloc it.
Do the memory out.
So as an example, like I have 10 arrays with 100 cost and computation want to ending one when it's needed. What I will do, send always memory, into memory if it can. Do all, I don't need to do malloc or copy many times. Right? I do everything at just one time. Send it back. Yeah.
So as a person, I want to tell you that on April 3rd, we'll have somebody with one of the developers and architects of mathematical, one of the libraries, so we in algebra. So if you come that day, you can ask them, okay, we don't know the sensitive application like that, application. I'll do that. And then you can ask them, how do it, for example, on mathematics, keyboard,
Because they have some of the from serial when we say from serial
conception of the algorithm. It is not the because an algorithm that is ready, it's working, you put it in parallel. It's not the way.
yes, some of the algorithms cannot be parallel, right? Like the Fibonacci series, I want to compute the Fibonacci from 1 to 100,000. I have one by one. Right.
Yeah.
Yes.
As I said, that's a lot of fun.
Yes. And so the challenges still remains like applicability. Can you solve your algorithms efficiently using GPU? Programmability, like effort for writing that is right? Means there are invariabilities between the and they are always able to get access to the last system. Do you have any system available with latest GPUs? And so if you have the very efficient code for one single GPU, how you scale it to the 8,000 nodes or 10,000 nodes, 3,000 GPU, possible, right? So these all are the challenges for running your code on supercomputer. Testing that my talk. I think we are Unity, right? You talk about one of the few CUDA applications here, a little bit more advanced in the CUDA program
Next.
in the next Tuesday.
So this